Hello everyone. So in the previous video we discussed how Qiskit's qubit ordering differs from what other references out there use. So we said, if for example we have some qubit order that starts here from top and goes down to bottom, in Qiskit, the way these qubits are organized in the CAD representation, they go from right to left. Whereas in every other reference you can find out there, if you have an ordering from top to bottom here, that order in the CAD is going from left to right. So what's important here is that the topmost qubit always ends up on the rightmost placement here, and obviously the bottom qubit ends up on the left, and in other representations the topmost always ends up on the left and the bottommost on the right. So we also mentioned that if we now replace this arbitrary names of A, B, C, D with the actual labels that Qiskit uses. So let's say Q0, Q1, Q2, Q3. Well, following that order from right to left, those qubits are ordered as Q3, Q2, Q1, Q0. And this is what is known, this type of ordering is what is known as little endian notation. So let's talk a little bit about what little endian notation is. So if we have a 4-bit number, and for now let's just forget we're dealing with quantum states. Let's just talk about regular bits. If we have a number, let's say in decimal, the number 10, if we're going to express that with 4 bits, well, that corresponds to the number 1010, right? So the way we organize bits in this representation is, well, we always put the most significant bit, so B3, on the left, and then the least significant bit on the right. So this is what we call the least significant bit, or the LSB, and this is what we call the MSB. Right, and that kind of makes sense, right? If we're gonna count in binary, the number 1 in 4-bit representation is given by 0001, then 2 is 0010, then 3 is 0011, and so on and so forth, right? So here, the number on the right is the one that is changing every time we increase the number, right? And that's what we call the LSB. So here goes from 1 to 0, then to 1, then it's going to go to 0 again. And only when we get to number 8, we're going to see the number to the left change, right? So that's the one that's going to only change after all the other bits have changed already, and that's what we call the MSB. Now, the other way we could represent a binary number is using what is known as big endian notation, big endian notation. And that's just basically the opposite ordering. So if we were going to represent again the number 10 in decimal, then that number would correspond to 0101. So here we just read the number from right to left instead of from left to right. So this ordering corresponds to B0, B1, B2, B3. So as you can see, this little endian notation is the most commonly used notation to represent classical bits, and that's exactly what Qiskit uses. So there's a good argument for using little endian notation. But that's really not what makes Qiskit different from every other reference. What really makes Qiskit different is the relationship between the bits in the CAD representation to the ordering in the circuit itself. So let's go through some of the examples that I had shown in the previous video to explain what we mean. So in the previous video, we had the following example where we had on qubit 0, we had no gates applied, right? And on qubit 1, we had a Hadamard gate applied, right? So let's take a look and see what state vector we get when using Qiskit notation. So let's write here Qiskit, and then after this we'll compare it to the way other references do this. So following again Qiskit's notation, we know that the most significant qubit is on the left and the least significant qubit on the right. And as always, we initialize the state in the state 0, 0, which is the same as 0 tensored 0. And then we apply a Hadamard gate, right? So let's apply our Hadamard gate, and we apply it to qubit 1. So let's put a little 1 here to know that it's applied on qubit 1. And since this qubit is qubit 1, then we're going to get 1 over root 2, 0 plus 1, right? So this is now qubit 1, right? Tensored with 0, because qubit 0 didn't change. And then if we distribute this, well, we get 1 over root 2, 0, 0, plus 1, 0, right? Now, in other references, and so let's here write other, it is very common to still use little endian notation, where the state vector still has the most significant bit to the left and the least significant bit to the right. What really changes is the order in which we organize the qubits in the circuit itself. So if we have the exact same circuit in the same order we're applying the gates, so let's copy that here. And in other references, what we will see is actually that the qubit on the top is Q1 and the qubit at the bottom is Q0. So if we still use little endian notation, which is, Q1, Q0, right? Same as what Qiskit uses, but now the order of the qubits is different. Right here, we're increasing from top to bottom in Qiskit, right? And in the other notation, we are increasing from bottom to top, right? So again, initializing this at 0, 0. Well, after applying our Hadamard gate, what we're going to get now is, again, we're applying it now on qubit 0, right? Not on qubit 1. So we get 1 over root 2. Oh, sorry. We get, since this is qubit 1 now, and qubit 1 has no gates applied, we get 0 tensored 1 over root 2, 0 plus 1. And clearly, the order here is different. So if we distribute this, we get 1 over root 2, 0, 0, plus 0, 1. So as you see, using the same little endian notation, but different order in the circuit, what obviously is flipping the order of the qubits here and here, right? Now, I did kind of mention that when we're talking about this other way of representing states or the correspondence between circuits and states, there are two approaches. There is another approach where we still organize the qubits from least significant qubit at the top and most significant qubit at the bottom. But in those references, what you will see is that now they use big endian notation to express the state vector in ket notation. So in that case, the way the qubits are ordered is qubit 0 on the left and qubit 1 on the right. And for example, Penny Lane, the quantum computing software platform, uses this type of notation. So what you will notice is that actually this is perfectly equivalent to this other one we just described, because if you're now swapping the qubit ordering in the circuit, but at the same time swapping the qubit ordering in the state vector, well, it's going to give you the same result. So, if we initialize at 0, 0, and then apply our Hadamard gate, well, now Hadamard gate is being applied to qubit 1, but qubit 1 is the second one in the ket, so we get 0 tensor with 1 over root 2, 0 plus 1, which is the same as we got before, right? 1 over root 2, 0, 0 plus 0, 1. So even though here we're using little endian notation, and here we're using big endian notation, because the order in the circuit is reversed, we get the same result. Whereas in Qiskit, we're using little endian notation, but we're using the opposite qubit ordering as what we did here, right? So that's what makes Qiskit different from everybody else. So now another thing to keep in mind is that the way we express unitaries changes, right? So for example, let's rewrite the circuit here. Let's again, you know, in Qiskit we have no gate on qubit 1 and qubit 0, sorry, and a Hadamard gate on qubit 1, right? So if we were to write the unitary for the circuit, right? So the unitary for that circuit, well, in Qiskit, we need to also flip the order in which we apply the tensor product or the Kronecker product to find the total unitary. So here, since the Hadamard is being applied to qubit 1 and our most significant qubit is always to the left, well, now we need to do the Hadamard gate first and then tensor that with an identity. And you know, the identity is there because not having anything on qubit 0 is the same as having an identity gate, right? So now if we do this, right, we have our Hadamard gate is 1, 1, 1 minus 1, and then tensored with the identity matrix, which is 1, 0, 0, 1. That's going to give us 1 over root 2, and here what we do is we multiply this matrix by each of the elements of the Hadamard gate matrix, right? So we can break this into 4 quadrants, and here we apply that identity multiplied by 1, so we get the identity, right? Now here on the bottom left, again, we're multiplying by 1, so we get the identity again. On the top right, again, multiplying by 1, so we get the identity. And on the bottom right, we're multiplying by minus 1, right? So we get the identity where the diagonal elements are minus 1. So minus 1, 0, 0, minus 1, right? So that's the final matrix we get, which is very different than what we would get in the other two notations, right? So the other one that we specify here, in both of those cases, the way we find that unitary, so this is Qiskit, and this is every other reference out there. In that case, the way we find unitaries is we would start with the one being applied to qubit 1 again on the left side, tensored with the Hadamard gate, right? And I'm not gonna do the exercise, you can do it, but you'll see that you get a completely different unitary. So that's important because when trying to figure out what the total matrix looks like when applying it to states is very different depending on what you are selecting to be both the order of the qubits in the circuit and the order that you're using in the ket representation. Now, another example is a CNOT gate, right? So in Qiskit, so let's do here the CNOT gate, right? In Qiskit, well, typically what we do is, well, the CNOT, if we're applying it like it's conventionally done from top to bottom, so here we have the control on qubit 0 and the target on qubit 1. Well, we can do a little table here, right, where we map state 0, 0 if we apply a CNOT gate, that maps to 0, 0, right? Because again, using Qiskit ordering Q1, Q0 for a state vector, our control is the qubit on the right, and here the control is on 0, so you don't change the target, so it stays at 0, right? But now if we have state 0, 1, and again we applied the CNOT gate, well, now that's going to turn into 1, 1, because this is the control and this is the target, so the target is changing, right? Now if we have state 1, 0, again, this doesn't change because control is at 0 and target is at 1, so we get the exact same state. And then if we have 1, 1, well, now control is at 1, so that's going to flip the target, giving us 0, 1, right? So we can build the unitary matrix for this, right? So if we do the unitary for the CX gate, well, we can treat this as a map, right? So we can say, here we put in the columns the input states 0, 0, 0, 1, 1, 0, 1, 1, right? And each element of that column is going to tell us what probability amplitude does it going to map to the state of the output. So we can put now the output states here in the rows. So 0, 1, 1, 0, 1, 1, and this here is 0. There we go. So if for example we're mapping 0, 0 to state 0, 0, well, we know we have a 1 here in this place of the matrix, and then we have zeros everywhere else, right? If state 0, 1 maps to 1, 1, well, we have a 1 down here at the bottom, right? Because that maps to state 1, 1, and everything else is zeros. 1, 0 maps to itself, right? So then we get a 1 here. And then 1, 1 maps to 0, 1, so we get a 1 here, and zeros everywhere else. So this is the unitary matrix that you would get using Qiskit's convention, with the target on qubit 1 and then the control at qubit 0, right? So I'm not gonna derive the unitary when you use the other notation, but you're probably fairly familiar with it. So this is here is Qiskit's notation, and then I'm gonna write here other representation, but you're probably familiar with it. It's 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and 0, 0, 1, 0. So as you can see, matrices are different with Qiskit notation, and this is what you would get with what we described before. So what I want to do next is now go into Qiskit and show how we can actually draw our circuits to keep the same convention that is used in other references. So let's go here and maybe go over a few examples, right? So let's do from Qiskit import quantum circuit, and then let's do from Qiskit quantum info import state vector, and let's import operator, and let's also import from Qiskit visualization, let's import array to LaTeX, right? So let's build the circuit we had before. So let's do QC quantum circuit, and we're going to have 2 qubits, right? And then we're going to do Hadamard gate applied to qubit 1, and let's go ahead and draw that. So here we go. This is what we had before, and let's now see the state vector representation for this circuit. So let's just go ahead and do state vector for that quantum circuit. And here we can see that we get what we had derived previously for the Qiskit notation, with that 1 on the left side of the cat, right? Well, if we wanted just to change this to the other notation, well, that would mean that we need to apply our Hadamard gate to qubit 0, right? But when we draw this, now the Hadamard gate is at the top, and what we had seen before is that to stay consistent in the representation, we want to order the qubits in the circuit with the most significant at the top. But this is just a matter of the way we draw things. So here in this Qiskit quantum circuit draw method, what we can do is actually do reverse bits. We can pass this parameter and set it equal to true. And that just changes the order of the circuit. And if we now take a look at our state vector, well, now we get what we had derived for this representation, where we still are using little endian notation for kets, but we're ordering our circuit with the most significant bit at the top. Now, for more complicated circuits, what we can do if we want to keep implementing circuits the way Qiskit does, but at the end just reverse everything, there's a reverse bits method also for the quantum circuit. So not just for drawing it, but to redefine it in the reverse way. So for example, I don't know, let's do a quantum circuit with 4 qubits, and let's apply a CX gate between qubit 0 and 1. Then from, I don't know, 0 to 2, and then a Hadamard gate on qubit, let's say 0, and let's draw that and see how it looks like. So here we have our circuit. Let's do something to qubit 3. So let's do a CX gate from qubit 1 to qubit 3, right? So we get this circuit, and if we wanted to reverse the order of this so that the gates are applied again, in this same fashion where our controls are above and our targets are at the bottom, but we want to use the other representation, what we can do is do a quantum circuit and then use this reverse bits method. And then what you'll see is that it will flip the circuit over. So now the controls are, in this case, in the most significant bits, and the targets are the other way around. But again, what we want is to draw this the way that we find more intuitive. So what you can do here is reverse bits equal to true, and that way we draw the same way. But if you compare them, I guess I got rid of the other one. Let's do this. If we compare this to circuits, where here we have the Qiskit notation, right? Where Q0 is at the top, Q3 is at the bottom. Now if we use this reverse bits, it flips the qubits, and then we draw it in the reverse way. We now have Q3 at the top and Q0 at the bottom. And this clearly will give, even though the drawing looks the same because the order is different, this will clearly give different state vectors and different unitaries, right? So if we go back to the example we worked on with just a C0 gate, right? Where we do just a C0, let's say from 0 to 1, right? Well, we saw that the unitary in this Qiskit notation for this quantum circuit, let's actually do here array to LaTeX to draw it nicely. We get that unitary that we derived previously, right? But if we wanted to get the unitary that we typically get in most textbooks, or pretty much in every textbook, well, we would need to reverse the bits here, and if we want to draw it in the conventional way, we set this to true again, and then we get that circuit. And if we now look at the unitary for that, we get the one we're typically used to. So that's it. So one last thing I wanted to mention is why would Qiskit organize things in a different way than what everybody else typically does. And there is some rationale to it, right? So if you think about it, organizing qubits in the state vector using little endian notation makes sense from the standpoint that that's what is typically done also with classical bits, right? It's the most common way of organizing them. There are a few exceptions, like in communications, sometimes they're reversed. But why use the reverse ordering in the circuit itself? And you know, a good reason is that typically ordering things from least significant to most significant makes it easier in terms of programming, and it makes it a little bit better to avoid having errors in your code. So for example, if we were to implement a function, let's define a function and let's call it to GHZ. Let's say it's a function that is going to define a circuit that generates a GHZ circuit, right? And it takes as an argument the number of qubits. Well, let's define a circuit with that number of qubits. Well, the GHZ circuit first applies a Halomar gate on qubit 0, right? So we're going to do it the Qiskit way. So we're going to apply it on the qubit at the top, which is qubit 0. And then we're going to do a for loop, right? For, let's say, for I in range. And we're going to be applying CX gates from qubit 0 to every other qubit. So we're going to do it from starting qubit 1. That's the first one that's going to be our target in the CNOT gates, to N. And then we're going to do CX from 0 to I, right? And then let's return our quantum circuit, right? So now if we call that function, let's define a quantum circuit QC. Let's call it, well, first let's say we want 5 qubits, right? And we're going to do QC equal to GHZ of N. And let's do QC.draw, right? Here we see our circuit for using the Qiskit convention, right? It was fairly straightforward. If we wanted to do this using the other conventions, it can get a little bit cumbersome and it can lead to some mistakes, right? So let's say now we want to do it the reverse way. Well, we would need to now apply the H gate to qubit n-1, right? Because the qubits start counting starting from 0. So the last qubit is qubit n-1. And then our for loop would have to go from the first qubit that's going to be a target. It's going to be the qubit n-2. And then we need to decrease the number of qubits, right? Because we're starting from the most significant going to the least significant. So then we need to go to qubit -1, because this range function goes to the number that is the non-inclusive up to this point, right? So that will be qubit 0 if we go to -1, and then we need to decrease by -1. So you see here, this can be really cumbersome. You need to think a lot, and leads to a lot of mistakes. It's not impossible, but you can think of having much more complex circuits than this, and it can lead to issues, right? But if we do this, right, if we do this for this new function, I just define again n is equal to, let's do 5 again, and then now we need to draw it with reverse bits equal true, right? We get the you see, and I made a mistake here, right? So I'm trying to apply the CX gates actually from I to, from n-1 to I. There we go. That should work. So there we have it. And you see, even I made a mistake. There was so many things to change here that it makes sense to organize things the other way around. So that's it. That's the rationale behind the way Qiskit orders its qubits and using little endian notation.